In this chapter, we're going to talk about some details about geometric modeling. And really, this is a big topic. We could spend all quarter doing nothing but this. And in fact, Professor Zhang in our department teaches a 1/4 class on geometric modeling. But we need to do some amount of this ourselves for Intro to Computer Graphics. Okay, so what do we mean about modeling? Modeling means building up geometry because we need geometry in order to draw things. And so, yeah, we need to build up geometry, but we need to ask these questions first before you start diving in and just drawing things is what do we need? What's required? Are we just simply looking at the appearance of something? Do we need to interact with a shape like pulling and pushing on vertices? Does this interact with its environment at all? Does it do some physics and bounce around? Do we need to know its mechanical properties, surface area, volume, center of gravity, moment of inertia? Is this going to need to be 3D printed? That is, you don't dive into things in computer graphics without thinking it through. Is what is it you actually need to do? Because that sort of describes how much information you need to build into it. And we're going to come back to this same idea when we do rendering and when we do animation, is you stop and you say, why am I doing this? And then that helps you define what it is you actually have to do. So we're going to look at some multiple ways of modeling geometry. And you can kind of guess by looking at them what they would be good at and what they would not be good at. Okay, the easiest way is a list of triangles, and that's known as a mesh. And you can see here as we zoom in on the bunny, well, in this case, it's a lot of triangle strips, but essentially it's a list of triangles. Sometimes if it's like triangles all over the place like this, it's referred to as a TIN, which stands for triangular irregular network. I guess mesh, TIM. Guess that didn't work. And so we come back to our cube example, the same thing we talked about when we did vertex buffer objects. Yep, it's tables all right. Tables of vertices, tables of indices, tables of color, could also have tables of surface normals, could have tables of texture S&T coordinates. It's whatever you need. But you explicitly list the geometry and topology. Or with triangles. So here we're, instead of quad indices, we're going to do triangle indices, and there's more of them, but there's only 3. And like we've talked about before, one of the big advantages of triangles is, by definition, a triangle has to be planar and has to be convex, whereas a quad is not necessarily planar and is not necessarily convex. So yeah, we typically do these kinds of meshes in triangles. 3D printing uses irregular triangular mesh data formats, TINs. And so here is a 3D printed object. And so really interest in TINs, triangular irregular networks, has increased lately because, well, that's how you get geometry to 3D printers. This particular one has a certain significance. Oh, look, it's a reverse of the Beaver Athletic logo. Well, why would you do that? Because if you make something like this, I did this by kind of manipulating the logo, but if you do something like this, oh, you can make beaver cookies. Yeah, okay. Gratuitous technology. Sorry. All right. Meshes can be operated on. Okay, one thing that's really important in meshes is meshes can be smoothed. So here's the monkey icon from Blender, and if we smooth it, we get more polygons, but we get smoother ones. Instead of these big jagged edges here, we get more gradual ones. And if we smooth it again, and we could smooth it again, each time you smooth it, of course, you get lots more vertices. But as you can see, you can start with something pretty crude, maybe something that you even sculpted yourself and digitally sculpted, and then smooth it out into something a lot nicer. So you don't have to start out with hundreds or thousands of vertices. You can start out with a lot fewer and then smooth your way to something better. You can edit vertices of a mesh. Again, this is a Blender example. Here we're going to grab one of these vertices and we're just going to pull it up. Now, what that does is it creates kind of this Mount Everest look on your sphere, and maybe that's not what you want, because typically we don't, but typically we want something a lot smoother. There is a editing technique called proportional editing, and if you turn that on and you pull on the same vertex, well, what you get is you get other vertices going with it like that. And you can see this very light circle right here. That's the circle of influence for the proportional editing. And if you move the mouse wheel, you can make that circle bigger and more vertices will start to get pulled. Or if you make the circle smaller, less vertices will start to get pulled. But now you have more of this very gradual pulling instead of an abrupt pulling. Oh, do you remember Venn diagrams from high school? That's probably what you called them. They are really 2D Boolean operations. That's not what we called them in high school, I remember. But they really were for describing sets and set theory. And in Venn diagrams, you had two overlapping shapes. Let's call them A and B. And if you take the union of A and B, well, you get this outer edge, this outer boundary. That's taking the combination of them. If you say intersection of A and B, you get the part that's common to both. And you probably didn't do this in high school, but we do it in geometry modeling, is you can do difference. So A minus B, it's like B has taken a bite out of A. Okay, now take what you learned in high school, what you're now struggling to remember, and work it up into 3D. So here's our two overlapping solids, A and B. The union, A union B, looks like this. A intersect B looks like this. And A difference B looks like this. The difference is really useful. If you can put holes in things, or you can basically make inverses of things, like make molds you pour rubber into by subtracting an object from a block. Difference is really a very useful thing. Union is useful too, and here's why, especially useful for 3D printing. A and B here in this original diagram are occupying the same space, or at least part of A is and part of B is. They're occupying the same space. Well, in real life, things don't do that. And so if you just take A and B together, occupying partially the same space, and send it to a 3D printer, the 3D printer will screw up. What you would do if you wanted to print that is you would do the union, because, remember back in the 2D world, what a union does is it leaves just this outer edge, well, in our case, the outer surface. And so because this union is now just leaving the outer surface, these things are not occupying the same space anymore. It's getting rid of what was separately in the middle, just like this was getting rid of what was separately in the middle. So yes, union and difference are really, really useful. And I use intersection every so often just to see if two objects are interfering with each other. That's how you find out. You take their intersection in the solid world, and if there's anything, then they're interfering with each other. Anyway, in the CAD world, this is sometimes called CSG, or constructive solid geometry. But essentially it's 3D Booleans. Yeah, here we're doing it in Blender, doing goofy things like taking a hole out of the monkey's head or finding the intersection of the cylinder in the monkey's head. Yeah, I can't think of a good use for that either. Okay, other ways of sculpting. We looked at the sculpting method where we could do proportional editing, and that was really useful. That was really useful because we could make a lot of vertices go with us by only pulling on a little bit. And in fact, this is really our mantra for interacting with geometry. We want a small amount of input change on our part, a small amount of work on our part to result in a large amount of output change on the object's part. And proportional editing did that pretty well. And there are other methods. This one's called a lattice or a cage. There's a video out on the website that I made just to show this because it's kind of hard to show in static pictures. But essentially what you do is you take something simpler like this box that's been slightly subdivided, you overlap it with part of your object, you attach it to your object, and then you start pulling on the points that are here in the object that's doing the surrounding. Okay, and as you do that, the object inside, no matter how many vertices, you could have thousands of vertices in here, no matter how many vertices you have inside that box, they will start to come with the points you're pulling on proportionally. And so this is a great way to stretch the rabbit's ear, for instance. And again, it is following this mantra that a small amount of work on our part is resulting in a large amount of change on the object's part. Here's another way that that can happen. This is known as curve sculpting. And in curve sculpting, well, what we have is we have some discrete points. And if we take those 4 points, and I'm letting the letter capital P mean X, Y, Z together, and we plug it into this equation, and we let T go from 0 to 1 in some increment, maybe 0.1, 0.2, 0.3, 0.4. Every time we use a different T, we're going to generate a different point that's on this curve. And if we connect them up with, say, like a line strip, we have a curve. Well, okay, instead of letting T vary from 0 to 1 by 0.1, how about 0.01? Well, now we would get a fairly smooth curve out of this. And if we pick up one of these points and move it somewhere, the curve is going to flex and change with it. This again, small amount of work on our part, just moving one of 4 points, results in a large amount of change to the geometric model. Okay, so if we would never vary t in increments of 0.2, but if we did, these are the points we'd get, and then we would draw a line strip which would look really, really coarse. So make your delta t smaller, and this is used a lot just for making smooth shapes. And so here's a smooth shape. And if I pick up points and move them, the curves change their shape, kind of go follow the points. So if I take this smile and I move these 2 points like that, the curve turns into kind of a sneer like that. Small amount of work on our part results in a large amount of output change. So we like that. This is known as a Bezier curve if it follows that equation. And what makes a Bezier curve is it starts at P0, it ends at P3, and it's influenced by where P1 and P2 are. So that's why this flower petal goes out like this. In general, the curve doesn't go through points 1 and 2, but it's influenced by them. Think of points 1 and 2 as gravity bodies sucking the curve out through it. There's another representation of curves I really like. And in fact, there are probably dozens of different curve equations, but I like the Bezier and I like what's known as Catmull-Ram. Catmull-Ram is neat because it does go through points. It's a great way for interpolating, doing a smooth interpolation of a number of points that you've thrown up there. But here's how it works. If I've got 4 points, And here's my equation, and it's got P0, P1, P2, and P3 in it, and I vary t from 0 to 1 in small increments. It will smoothly draw a curve from point 1 to point 2. Point 0 is really there just to sort of influence how the curve gets started. Point 3 is there really to influence how the curve ends. But what's fun is if you connect these together. So let's say I've got 6 points. Well, points 0, 1, 2, and 3 will generate this curve right here. But we're not going to stop there. Now let's take points 1, 2, 3, and 4. And they together will generate this curve right here, which is first derivative continuous with the first curve we drew. Now we grab points 2, 3, 4, and 5, and together they generate this curve, which is first derivative continuous with the middle curve. And so we can take any number of points, apply the Catmull-Ram equation 4 points at a time, and basically generate a smooth piecewise cubic curve through the points. Okay, it's sort of like having your own drafting tools for that. And you can play the same game with the same points. This is just like we did with the Bezier curves. 0 and point 0 and 5 are back here. 1 is here and 2 is here. So here is one of the curves that got drawn. Here's one that got drawn. Here's one that got drawn. So the advantage of the Catmull-Ram is the curve goes through the points. That's why I like it. Turns out you can also extend the same idea into the world of surfaces. A Bezier surface, the curve has 4 points. The surface has 16 points. The surface, when you run the equation, goes through the 4 points in the corners, and it's influenced by the other 12. And just like before, I can grab this point and say pull it up like this, and the curve will or the surface will kind of go up with it. So it's got the same ideas of sculpting as the curve does, only there's more of it. There's 16 points to sculpt instead of just 4. And you can also do analysis on it. That's kind of fun. You can do analysis on surfaces done this way. Because, well, gosh, you have the equations. We can do things like draw contour lines. We can show curvature. These arrows are showing directions of principal curvature, and the colors are showing how steeply it's curved. So it's great. Not only can you play with appearance, but you can play with analysis. You can play with the analytics of the characteristics of that surface. So that's the first part of the geometry modeling notes. I've broke them into 2 pieces just to keep any one of them from being too long. And so come back for the second one.